So, welcome everybody. I'm just going to start introducing myself and the event. And in the meanwhile, we're going to give people 30 seconds to a minute to keep joining. So, my name is Justin. I'm here today with Mark Anderson, who's going to introduce himself shortly. So, we decided to do this event on design of experiments to get some insights from Mark, who's been working in this area for a long time and who's an expert in the field. And the reason I got interested is as a consultant recently, I've been dealing with more and more complex designs, a lot of work in field experiments, medical experiments. But when I started learning about it, I saw that there was this big area where we use this in very complex experiments for manufacturing and process control and things like that. So I was interested to learn more about that and kind of show that these principles that have been around for a long time are still very useful in many industries. And I thought it would be great to have Mark to discuss this. So, Mark, thank you for joining. I'm very happy that we can do this now. Could you maybe start with explaining us your background? I know you're not traditionally from a statistics background, so I would be very interested to know how you got to learn statistics, what got you interested in the first place. So,
sure. Yeah. Well, thanks, Justin, for having me. This is a really cool technology to have a live event like this on LinkedIn. So I'm pretty excited to be a part of it. We've been doing our training since March of 2020, pivoting from doing in-person, going back decades, to just quickly getting set up on Zoom. And ever since, we've been doing training at a distance. It's really opened up the horizons tremendously. We're doing a lot more work with people in Europe and throughout the world than we ever did. So it's just really fun to be connected up, talking to primarily industrial research and development people, people working, graduate researchers, things like that. So I spend a lot of time, talking to people like this across the internet with the video, audio. And I love it because I love visiting with people.
Yeah.
And so, my background, really my interest goes back to as a child, as the son of a master civil engineer, grandson of an engineer, and with the Anderson Swedish engineering heritage, I right away took to, quantitative type endeavors. And I also have always been interested in multitasking, and hence the idea of doing design of experiments, and which I promote as a multi-factor approach as opposed to one factor at a time, has always had a tremendous appeal to me. And for example, I would, when I was delivering papers, I would consider I could go straight up one side of the street and down the other, or I could go back and forth. Rudimentary, simple comparative experimentation without, knowing anything about statistics or anything. Later, when I was working in a hospital, as I worked my way through chemical engineering school at University of Minnesota, I realized that when I pushed carts up into the different floors of the hospital, I could throw 2 carts into the elevator, which probably wasn't very kind to anybody else because it blocked it off, run up the stairs, pull them off, and I could get the work done in a fraction of the time. I spent some time at Michigan State University, and I was on a work study program, and I had to vacuum the floors. And I kept working on, ways of making it faster and better until I could get it done in a fraction of the time and go back and take a little nap after, late night activities in college.
Yeah.
So this was kind of my approach to things. So that when, as a chemical engineer, I started working with General Mills Chemical R&D, they introduced me to the use of multi-factor testing, 2-level factorials, other approaches, the use of statistics, regression analysis. This was all at a very mature stage when I started as a summer engineer in 1974 at General Mills Chemical. So I consider myself to be very lucky, being the son and grandson of engineers, having gotten a job at General Mills with the agricultural heritage, had been connected up with the agronomists that Fisher worked with in Minnesota going way back when, and to the chemical process industry. So for me, it's always been a very natural fit.
Okay, good. I wonder what was faster for delivering the papers? Was it
going back and forth? But
Yeah.
you know what? The thing is, when you do an experiment that involves yourself, it gets terribly biased because you naturally have some preference for it.
Yeah.
So I'm pretty sure I was running back and forth when I went back and forth as opposed to walking up and down. And that probably was the reason the effect worked.
Okay, so first insight that you need to be blind, or you need to use a different comparison group.
No doubt. I mean, the double blind gold standard, I'm very much a believer in that if it's involving people.
Yeah, of course.
Right.
Okay, thanks for sharing. So, so as you mentioned, you have chemical engineering background. So how does design of experiments fit into that area, or at least through your career or in general?
Well, it's an absolutely unbelievably effective tool for process development. Okay. So I would get from the chemist, typically a PhD organic chemist, some kind of magical formula in a beaker. And my job was to scale that up through pilot plant, possibly semi-works, and up to the full-scale manufacturing. But there's a fundamental rule that you can't scale everything up. And the most obvious thing is to consider the surface area of a vessel to the volume of the vessel. As you expand the volume of it, that surface area is not increasing at the same rate as the volume is. So this creates lots of problems with mass transfer of chemical reactants and so forth. And the considerations of agitation have to be considered because you're starting with a little stirring magnet, and now you're going into some kind of impeller, like a little boat motor. And then eventually you get to a giant 2,000-gallon reactor to some huge big thing that's spinning around inside at a very slow rate, but mixing things up. So then it was a question of taking whatever the chemist gave me, and they would say, we want to do it at this temperature, pressure, concentration, and then the stirring magnet has to go at a certain rate, which I would always laugh at. Okay, so I'm going to take that as my center point around which I will vary each of the different factors high and low, and I'll form a two-level design with the center point being the standard conditions that the chemist gave me.
Okay.
All right. And so then I could quickly do what I consider to be a process sensitivity study. All right. Okay. So I would basically recalibrate at each stage of the process development these different factors that, might be, they say 5 factors. I would typically do a 1/2 fraction of 16 runs with 4 center points in a randomized plan. And I would learn, basically the design space, what's going to happen within that whole region, and reset my sweet spot as I moved up all the way through to the final manufacturing, if it lasted that long, because a lot of the projects in research, you get used to this, they don't work out. You just can't, do it and give the quality of product, yield, and all the attributes you need to have a successful development. So then I always said that we can use design of experiments and multi-factor approach to fail fast. Yeah. Right. So we'll fail faster. And also then we can write up a technical report one way or the other that will allow somebody in the future that kind of revisits this to start, from a higher level and stand on the shoulders of their predecessors and move up from there. So having a good report and one that was based on statistics that was valid, from the point of p-values and so forth. Yeah. All of this led to a very systematic approach that I came into with General Mills Chemical, that this was already mature at this point, coming from General Mills proper research to the chemical division. And that this was the way that the engineers were expected to operate.
Okay, interesting. So you mentioned a few technical terms like factor levels, runs. Would you mind maybe just clarifying for the audience what exactly you mean? Because I know that in different fields we use different terms. So
Right.
maybe clarify what you mean by two-factor and things like that.
Right. Well, one of the things I learned over the years was being, fairly concise with, I call it the jargon of our field of design of experiments for industrial R&D. So you think of variables, and you can think of input variables, and you can think of output variables. And as a chemical engineer, I think of a unit operation. I basically draw a box around, some part of a series of steps that I think is the critical step to work on. And inside that box, there's a process. And coming into it are input variables that I can manipulate. Those I call the factors, because those are the things that I'm going to change during the experiment. Other input variables I'm going to hold fixed, of course. And then there could be some things like humidity and temperature that I can't control, but I would record those and monitor them. And potentially I could regress them back out at the end as covariates. Okay? Then on the outside of the box is coming out of it is a response. It's what I'm going to measure. And for chemical products, it would be typically the purity, the yield, other attributes, things like that.
Okay.
And so the goal of doing the design of experiments is to create a mathematical model to predict the response as a function of X, right? Because if we can manipulate the input systematically, we can create insights into cause and effect relationships, use statistics to make sure that what we see is not just caused by chance, but is probably real. And so we're going to use our P less than 0.05 rule, right? And then if we succeed by having the right factors far enough apart to generate a response that changes significantly, we can then create this mathematical model using regression fitting. And then we can use that to identify, where we want to go next. We may, with a factorial design, where we're changing only things at two levels, push off to some corner of, if you imagine a square or a cube, 2 to the 2 or 2 to the 3. We're going to push off to some corner potentially, unless we happen to get lucky and we're centered right over the ideal spot. And that's why I want to run the center points.
Okay.
But usually you end up going through a strategy of experimentation, screening down many factors, identifying vital few, doing the in-depth characterization to understand interactions of things. And then ultimately you may go to a full response surface method, which is at least 3 levels of each factor. And then your model is going to be a polynomial model that has squared terms in it, which is called a quadratic. Then you can fit, peaks, you can fit valleys, you can fit saddle points like Pringle potato chips surfaces. And it's just a fantastic tool, for chemical engineering process development. But then beyond that, any process industry and manufacturing. So any kind of R&D, and I like to look around me and I like to say, we could be working with a ceramicist that's making this cup. We could be working with, and I've worked with people that are working with the surfaces on these phones.
Okay.
Paper and pulp, it just goes on and on. Every single product that you work with is developed and it's constantly improved, and DOE is a perfect tool.
Very interesting. Thanks for sharing. So before I get to the next question, just want to remind everybody, so we have quite a few people live, so thanks for joining, and feel free throughout the talk to put your questions in the chat. We're going to have a Q&A at the end. Of course, you could also just ask the questions at the end, but you might forget them. So just put them in the chat and we're going to have a log of them. And at the end, we're going to address those questions during the Q&A, so for 15 to 20 minutes at the end. Okay, so I know now that you work at a company called StatEase. It's been quite a while that you've been working there. So maybe you could tell us a bit about the company, what you do there, and maybe a story about how that company operates and how it started or things like that.
Right. Well, I mean, first of all, the name of the company, StatEase, and our slogan, Statistics Made Easy, was a bit whimsical because, of course, most people hate statistics. And the idea that statistics can be made easy is like an oxymoron. It's impossible. But that's been our goal from the start. And I have to credit Pat Whitcomb, who is a fellow chemical engineer, also University of Minnesota graduate, for being the founder of StatEase and really being the main force of it. So what happened was that our chemical engineering group, had fully embraced the use of statistics and design of experiments. And we brought in a professor from University of Minnesota to teach the group, more details on statistics. The first professor we brought in, though, was very pedantic, wanted to do a lot of derivations of things that we didn't care about. We just wanted the practical aspects.
Mm-hmm.
The second professor we brought in was Kinley Lawrence, who was the first advisor for Staties Incorporated. We're celebrating our 40th year from 1985 when the company was incorporated. But Pat actually started it up in 1982 in Minnesota, filing with the Secretary of State the name of Staties. So it goes way back beyond the 40-year anniversary we're celebrating of 85 incorporation. Beyond that, to the early 80s, and then really goes back to 1974 when I first started working with Pat. And we did these training sessions. And when Kinley Lawrence came in, he was much more focused with a little bit of coaching for us. And we had very good success in training new engineers in on these tools. At the same time, the computational facilities were improving. So originally we would use General Electric timeshare computers, and we could maybe do a rudimentary plot with little, typewritten X's and zeros and try to make a plot with that. But eventually, of course, the IBM PC came out. When that happened, Pat and another fellow worked out a way to program some very simple things from the book Statistics for Experimenters. Okay. And this was written in 1979 by Box, Hunter, and Hunter. This happens to be an autographed copy that I got from George Box in 1996 when I took training at the University of Wisconsin for a week. And he came in along with some other people and taught a class. Well, that book laid out the templates, things like Yates' algorithm for doing the calculations for a 2-level factorial array and so forth could easily be programmed in with a menu-driven package. Okay. So this was done by Pat when he founded Staties, and the first package was called Design Ease, and it was on a 5 1/4 floppy disk, and when I first, I helped him start the company because at that time I had my MBA. I got my MBA in 1980. Okay. So I kind of migrated into product management, marketing, other functions with General Mills Chemical that then became Henkel of Dusseldorf, which was a strange switch for people in Minneapolis, St. Paul area, used to working with General Mills and now working for a German company. But it worked out great. And so I helped Pat from the marketing perspective. Early on, we'd meet at McDonald's and I would talk to him about, we used to send out these card decks that you could subscribe to with magazines like Chemical Engineering News. So I helped him market the product, and then I joined Staties full-time in December of 1988. Okay. Now, along the way, of course, you went from the floppy disk to the more rigid 3.5 inch disk, and eventually, of course, just disappeared entirely. But all along, the computing facilities have increased in power. Yeah. And at the same time, our software has, improved over the years to the point now where it's unbelievably powerful, what it can do in terms of design and analysis of experiments.
Okay. So today, Staties kind of provides that facility or that capability to companies that are interested in doing more advanced DOE, or what would you say the market is for Staties?
I mean, when you look at, if you were to do some searching on how many chemists, how many engineers are graduated every year worldwide, it's a huge number. Now, not all of them are doing experiments, but anybody that's doing an industrial experiment is a candidate to use these multi-factor approaches. Unfortunately, the universities don't train people in. It's very rare that this happens. I'm working with the South Dakota School of Mines, and I did a semester-length class for their chemical engineering group, students and graduate students. I've been working with them for about 20 years now, but that's pretty rare. Most of the universities like Minnesota, they want you to learn the first principles of things like chemical engineering, mass transfer, heat transfer, chemical kinetics, and all that.
Mm-hmm.
And then they throw you out into industry, and maybe you go to work for R&D, and all of a sudden you're confronted with something that, you can't get out of a book. You have to start doing empirical studies.
Okay.
And since you don't really know anything about design of experiments, how to lay out a good experiment, or how to look at the results and deal with variability, you're just ill-equipped to do anything. So then Stati steps up, and there's some other companies out there as well that are in this field of DOE.
Mm-hmm.
And we're able to provide training, software, and then we do a lot of consulting. But as part of our pricing model, I'm at the point of helping people that are licensees. And so I oftentimes will take somebody in. Like yesterday, I got a call from research and development for a flavor company in Chicago, and they're trying to reduce the amount of sugar that goes into the foods by putting enhancers in. And so she set up a fairly complicated mixture design, which is dealing with components. And so I can help people like that. Some of it's email, some of it's face-to-face. And like I always say, we're trying to teach people how to fish, but not to fish for them.
Okay.
Right? So we're trying to put that power of design of experiments in their hands with the tool of the software, but also a lot of educational resources, the tutorials in the software, the help system, all the YouTube videos. And then if they really want to get going, they would employ us as trainers.
Mm-hmm.
But we'll also do a lot of hand-holding. And since the people we work with are extremely bright, they learn very quickly, and they don't want to come and ask for help. But they're also smart enough to know they need to at the start.
Yeah. Yeah. So it's people that already have technical backgrounds, so they have the maturity to learn the material. Yeah.
Right.
Okay. So my next question, it's kind of two-part. Do you think that design of experiments is underused in industry? If so, why? And related to that, what are the signs maybe that a company or a team could benefit from it?
Yeah, I think it's terribly underutilized. I think it's a travesty that more isn't done at the engineering and scientific schools to equip people with the know-how of dealing with variability and to lay out a good multi-factor or multi-component plan. And so on the one hand, it's a travesty. On the other hand, it's an opportunity for Statis, and we just continually are working with people coming out of school that know they need something better to do, and so it's like a never-ending stream of people that don't do DOE, that need to do DOE, and not a large fraction of people recognize that, but enough do that it makes it really worthwhile. For example, another encounter I had last week was with the company that makes bike locks, and they make these U-shaped bike locks. You've probably seen them.
Yeah.
And they have a special coating, and I forgot what the name of it was, but they put a name on it. And finally I said, I don't think that's a chemical. And the guy I was talking to said, no, we just made up that name because we can put this coating on this bike lock. And we've got videos from some of our clients. The thief comes in with a little battery powered disc and he's expecting to be able to cut right through that. But the first thing is when he puts that disc up and starts spinning it around against the surface, the disc breaks apart. And he puts another disc on, and then finally the battery goes out, and he goes away and steals some other bike that has a different lock on it. Well, this guy says that he's bound and determined to embrace this multi-factor DOE approach because he's tired of hearing from people that are going to go do some research. And when he asks them what they're going to do, he says, well, we're just going to fool around a little bit and try some stuff.
Yeah.
And that is not a good approach.
Yeah.
It oftentimes will work just because of sheer persistence. Like Edison, operated on 99% perspiration and 1% inspiration. He just worked and worked until he finally came up with a light bulb, so that can work. Mm-hmm. But No, I think I don't know what the percentages are of people that know about design of experiments coming out of these high-powered schools, but it's got to be very small.
Yeah. So you would say that, which was kind of my next question, like people that don't use design of experiments, how do they solve their problems? They kind of use experimentation that is not guided or not well done or very costly.
Yeah, I mean, what they're going to do is a scientific method, which
Okay.
goes back hundreds and hundreds of years, maybe to the time of the Greeks, that realized that if you're going to try something, you should hold everything constant and vary only one thing.
Mm-hmm.
So at the very least, if they do that, then they can draw these profiles. Like the chemist I would work with would test factor A, which might be temperature, and he would say, well, I can see there's a peak of yield here on A. So I'll set A at this level. Then he would turn his attention to B while A was set at the right level, do a profile on that. But it could be that he's just cutting across a rising ridge, which you'd have to do at least a 3-level experiment, like a 3 to the 2 power experiment, and then fit a polynomial model that's a quadratic with square terms. And then you could see, and in one case, the chemist had done this, and for this natural vitamin E product, had said that the most we can get for yield is 77%. And when I went through a more systematic multi-factor approach, I was able to get it to 95%. And that was worth $2 million a year to General Mills Chemical.
Okay. Yeah. So,
so that people are missing out on the combinations of things, right? Especially in the process industries, but it's also true in any manufacturing situation that it's oftentimes not just one thing or the other thing, but it's the two things together that are either synergistic and you can get more out of the two things than you could from either one alone, or it's antagonistic and they're working against each other, and you want to know that.
Yeah. Okay. Thanks for sharing. So my experience with, so you were talking about how this is done in schools, I guess, mostly engineering schools, or at least in people that get some sort of scientific training and end up working in industry. So my background is in math and stats, and my design of experiments class was a bit like you were saying earlier about the very pedantic teacher and deriving a lot of complex equations, and I never really understood, like, why would we care about this. There was no context. There was a lot of very complex, like, triple sums for these sums of squares and these complex designs. And yeah, all that to say, I didn't enjoy it that much. So I imagine when you started learning it, maybe you were confronted to some of these kind of ways of doing the theory that are very theoretical, very mathematical. And I know that you eventually wrote your trilogy of books. So I was interested maybe to just know about how you kind of decided to do that project, what motivated you, and the titles are DOE simplified. So what exactly are you simplifying? And yeah, maybe you can just tell us a bit about it. And in the meanwhile, I'll share a link for people that are interested in just checking out the books. So maybe you can expand a little bit on that story.
Yeah. Well, I mean, first of all, I again want to pay homage to Box, Hunter and Hunter, 1979, and they did finally come out with a second edition. But I had a chance to train with George Box. I met Stu Hunter at some conferences, and so definitely standing on the shoulders of them and George Box, being the son-in-law of Ronald Fisher. We go back to Fisher, and Fisher connected up with William Seeley Gossett, who developed some simple comparative experiments, the t-test, t-distribution, Fisher with the f-test and the 2-level factorial designs and all that. Box inventing response surface methods in 1951, and then writing this book that was very inspirational. And then beyond that, I also have to give a lot of credit to Doug Montgomery, who kind of carried on. This is the 7th edition of his books, but I think he's might be 9th or 11th editions. And I had a long collaboration with Doug Montgomery, who's still somewhat active at Arizona State. Well, those two books are really well written, but there's still a little bit too much information for people that just want to know what they need to know to do the design of experiments. So what I did was I took our training class, Experiment Design Made Easy, which, again, giving credit where credit is due, Pat Whitcomb, did a lot of heavy lifting on this. But Pat would carry the books all the way through, or the materials, to a certain point, and then he would get kind of bored with the last part of it. That was the fun part. So I was always the guy that would take what he did and try to keep it simple and make it fun. And so then finally I said, there's books out there, simplified, or DOE, or, books for dummies and things like that. So I approached a publisher called Productivity Press that was involved with quality tools like statistical process control, things like that, at a quality conference. And I said, I think there's an opportunity to write a book on design of experiments in a simplified, fun way. And they bought it. And it's currently in 3rd edition. And it's actually in print beyond Productivity Press, CRC Press, which is Makesberry's handbook, and a lot of books in the chemical industry. And then the overriding group is now Taylor and Francis, which is a big technical publisher. So this came out in 1999. And then I was very lucky that during that time frame, Six Sigma quality movement was building up. And so a lot of the Six Sigma programs picked up on this book for the DOE tool for their green belt, black belt, and so there was a lot of copies sold, and that kind of led to a 2nd edition, a 3rd edition. Then the second book came into play. It's actually got a fellow here at a petroleum refinery. I did work at an oil company, R&D, for a while. This would be a prime area where you can really get the most yield out by doing a more sophisticated response surface method, by doing multiple levels of each factor and really trying to get a peak of performance. This is in 2nd edition. And then the third book, which is actually is kind of my favorite, is Formulation Simplified. And the reason is that this addresses mixtures of things like a milkshake. We want to make sure we have just the right amount of milk, fat, sugar, chocolate, so the young kids that are drinking this will love it. And my mother, who's still going at 95, but we're trying to keep her fed. And the other night, I brought over a milkshake from Culver's, and she liked it, So somebody is doing a good job of mixing up those milkshakes, but that takes some science. And so then when you do an experiment, you want to do it in a multi-component way rather than one component at a time. But the neat thing about the mixture side of things is you work within these triangles. They're like phase diagrams, okay?
Yeah.
Each of the corners represents 100% of the ingredient that's, say, for example. So we have chemical A at the top and chemical B at this corner and chemical C at this corner. And then the triangle keeps the total always fixed at 100%. So once you know any of the two of the ingredients, the third is fixed.
Yeah.
And I thought that was the greatest thing since sliced bread. When I first saw it at University of Minnesota in my undergraduate, because the chemical engineering is combined with material science. And so you think of iron, nickel, and chromium at the corners of this triangle, and you want to get just the right formulation with 74% iron, 18% chromium, 8% nickel, or whatever, to get stainless steel flatware. Somebody did a lot of work to figure that out.
Yeah.
But now with the tools that we have in STADE software and using the mixture design tools for designing experiments, you can much more quickly identify where that sweet spot is.
Okay. Thanks for sharing.
Yeah.
So I want to ask one last question before we jump into kind of tools and resources for people that might be new or might be interested. There's a lot of talk about AI these days, and I was wondering how this fits into the evolution of the field. Is it helpful outside of, of course, it probably helps for administrative tasks, but the core science or the core principles, can they be accelerated or enhanced with AI? So what is your experience regarding this?
Well, I'm kind of in a wait and see attitude right now.
Mm-hmm.
I know everybody's really excited about AI,
Mm-hmm.
but I've also seen over the decades people getting excited about something called neural networks or other types of machine learning tools that's been around, and really regression analysis going way back.
Mm-hmm.
The idea that you can just pour a bunch of information that's been collected at chance into some machine, and then it's going to come out with a really strong output that tells you exactly what to do is really kind of an ongoing pipe dream.
Mm-hmm.
No matter what you call it, whether it's called neural network or machine learning or AI, I just don't think it's ever going to work without having somebody who's got actual intelligence, AI, that's behind it, that's got the experience. But I did see where Google is now touting within the last couple of weeks that we've now entered the AI age of inference.
Okay.
And so I had to look up the word inference, and the dictionary says it's a conclusion based on evidence reasoning, which is good. I mean, if you have a AI that it has got the capability of drawing inferences, that would really be something, right? Because now you're really talking about replacing an expert like myself, with an AI machine. But when that's going to happen, and if it ever happens, probably will, but we're still a long ways away from that.
Yeah.
So right now in the field of DOE, I think that people are always tempted, and this happened to me even way back when, 50 years ago, when I would go down to the manufacturing sites. And I said, I know you guys can get better yield out of your product because we know that that's theoretically possible. You're not doing things right. And so I want to come in, and I've gotten the highest authority from the top management to do so. So they agreed that they were going to let me in on the manufacturing site, but they said, just don't change anything. Well, I'm not going to be able to do any experiments then. Well, what am I going to do? They said, well, you've got these fancy machines that can take data in and give you something really strong. And so we've got all these records in production. Just put those into the machine and it'll tell you what to do. Well, it was what we call garbage in, garbage out, right? And so because the data was not very good to start with, it was, highly correlated and didn't really generate much of a shift in response. So I'm a little bit worried about AI just as kind of the newest thing on the block, that people are I think people are expecting way too much. But on the other hand, I've seen some studies on AI that say that if you look at scientists and you look at the top level of scientists that know what they're doing, they're the ones that are going to make the good use of AI.
Yeah.
It's the ones at the lower end of the spectrum that are not as bright and not as capable that are not going to get advantage of AI because they're going to get garbage in, garbage out. But the people that are at the top levels of science and engineering, they'll be able to probably leverage what they know about things with AI. But I still feel like design of experiments where you're doing a systematic layout that's orthogonal in a matrix of two-level design, for example, if you take that information and you feed it in, I talked to a guy at 3M one time who was doing neural networking, and he said that they succeed if they feed the machine a rich diet of DOE data.
Okay.
Right. And maybe they're throwing other things in there too. But if you don't have good nutrients in the feed, you're not going to succeed.
Yeah. And you probably, at least not yet, we're not at the stage where the experiment can just be designed and run by the AI, right? It's going to need a lot of considerations that are difficult to formalize or capture for the AI model.
I mean, hopefully the AI will know that we've got this new system and we want to figure out how to make it better, that we better run a good, orthogonal matrix, two-level design or whatever the particular combination of inputs is that will allow you to learn most quickly. The AI would know that.
Yeah.
So, maybe we could just lay back and sip our mint julep on the front porch and let the AIs do the work someday.
Yeah, and related to the AI and what are some things maybe that innovations or developments or recent trends that you're maybe more excited about, or that you think have more you have more optimism, or maybe things that happened in the last 10, 20 years in the field that you think are shifts toward more impactful design of experiments? Do you have anything that comes to mind?
I mean, I think what's been exciting to me to be working in this field for so long is that there's been, some tremendous developments in pharmaceutical, and particularly biopharmaceutical, where the bugs are making the drugs.
Mm-hmm.
And also then cell-based meats and fish and things like that. So I think, to me, the exciting thing is biotech, and what's been going on there in a lot of different areas, and there's still so much potential. And the thing is, though, that the tried and true methodologies, I mean, going way back to Fisher in 1920s, or even the simple comparative experiments that was being done by William Seeley Gossett, I think that to me, the cool thing is to be able to inspire these people, particularly in biotech, but in a lot of other industries, to embrace a more empirical approach to things, and try to use their high level of knowledge that they've gotten from their education in conjunction with these empirical methods, and don't be suckered into the idea that you can just fool around and do whatever you want, take that data and just pour it into some AI machine and get some brilliant insight coming out of it.
Mm-hmm.
You're going to have to do your work on it. You're going to have to, be methodical about your approach. There really, there have been some new developments. For example, Gaussian process modeling is something that we added in with our StatEase 360, which is our flagship product. And we've got tools there for working with computer simulations. For example, I did a training session for U.S. Space Force a year ago, and they're doing their work, using computer simulations, but they're stochastic. They have some, variability built into it, and then they're applying design of experiments tools against those simulations to come up with a transfer function. In other words, the simulation gets them into a certain point, and now they can run this little experiment on it, get a function out of it, and you can either use the standard polynomial models, or you can use these Gaussian process models. But that's obviously a very high tech area at this point. Mm-hmm. But I still I still like the idea, and I did do some work in bio. I worked on a fermentation of a product called Xanthomonas campestris, which produces a thickener that you have in your salad dressings and such, called xanthan gum. But I still think the old-fashioned scientific lab work that needs to get done is still really, really important, and using design of experiments for that.
Yeah. So thanks. So just want to remind you that there's the Q&A session. We're going to start it soon. So if you have any questions for myself or for Mark, just put them down in the chat. And while you do that, I'll just share a short story about. So I work with a biotech client, and they are very keen on experimentation. And it's been really fascinating. I can't go too much into detail because it's kind of secret stuff, I guess. But it's really fascinating because their products are kind of designed for use in the real world. So the experiments they have to do are less controlled because they're out in the field. That brings a lot of technical difficulties with the experiments, with the costs of running the experiments. And I was just wondering if you had any insights about how do you kind of balance these statistical or experimental principles of rigor and of control with these constraints of time, money, these uncontrolled environments. So I guess the quick answer would be, well, you develop judgment and expertise with experience, but do you have maybe any nuggets of wisdom or any practical insights about how you kind of go about doing these trade-offs?
Yeah, I mean, you want to guard yourself against getting too caught up in the statistics part of it, and you want to be very mindful of when a situation arises where you're actually getting pretty close to where you need to be, but you begin to recognize that there's probably a multivariable situation going on. And as you're kind of stabbing along, trying this and trying that, and trying to apply some judgment to it, you're just not getting to where you need to be. So just in time, is when you want to bring out these tools, and you always want to do the smallest design of experiments that you can. We used to call it the 25% rule, put no more than 25% of your budget into one particular experiment. But at the same time, and I know you've covered this in prior sessions, on power calculation and sample size estimation, right? So I always have to be careful to get people to guard against doing too small of a set of runs, and trying to understand what kind of power they've got based on the difference that they're trying to detect, or the signal relative to the amount of noise. And when you get a lot of noise relative to signal, then you're going to have a lot of averaging and a lot of replication, right?
Yeah.
And so it's really hard to say, what to do at any given time. You just have to kind of reassess. But if you're aware of these design of experiments tools, and you have enough know-how of when probably they would be helpful or when they wouldn't be, because it's going to take too much time or you have too much variability. So it's really, I think it's important to be well trained on these, if you're doing development work, on the DOE tools, and training up to a high enough level that you know when not to use it, that circumstances just aren't right. And so we just have to try to apply good scientific and engineering knowledge and hope that we get lucky.
Yeah.
At that stage. So I don't, I think oftentimes yesterday I was talking to a fellow and I said, I don't think you need DOE. And I was probably I shouldn't be going on a video saying this because, I'm trying to do my best for Statties. My son is the head of the development team. And so, we have a stake in this, but I really think it's important for people advising to be, honest about it and say, you're really not at a stage at this point that you need this, but keep it in mind. And one day you will be at that point.
Yeah. Yeah. So that's my, that's kind of the insights I had. So I think this company I'm mentioning is, I'm working with the head scientist who's sophisticated enough to understand the goal of experimentation, but it's always, for example, the principle of computing the power, right? Estimating the sample size you need. Well, in these complex settings that I'm working with, it's not, I can't just use a plug and play formula. So I use simulations, I use historical data to estimate things. And it's a lot of work, and sometimes it's a hard sell for the engineering team to put budget into this when they just say, why don't we let's just put 10 out in the field. We're going to know. But it's hard to explain to them, no, you will not. Like, you will get misled by noise, probably. And then we convince them to do the actual simulation, and we get some, oh, well, you're going to need to do 60 replications, and they were planning on doing 10. And sometimes it's very hard for them to wrap their heads around these statistical issues. So probably you face the same sort of pushback, or having to kind of sell the need for some of this work.
Well, yeah, and I think sometimes the real answer is that some of these companies need to invest more in research facilities, where they can do things at a lower scale, because then if you can work at a lesser scale, like we would do in the chemical industry with the pilot plant or the semi-works, you can work out a lot of these, questions beforehand. But there's always this leap to the field, to the manufacturing.
Yeah.
And then things will change, and it's really hard at that point to do anything further because, like I say, when I showed up at the plant, do everything you want as long as you don't change anything, because they don't want to create, information. They just want to make good product.
Yeah. And in this specific case, right, it's biotech, so there's living material, a lot of difficult variability to control for, even if you use some very tight processes.
Yeah, one of my jokes way back when was the person that was objecting to using statistics because his data was too variable to use statistics.
Yeah, exactly. That's funny.
But that's really what happens, and I don't know. You can only go so far, and what I've seen when I've actually did a little experiment with a high-powered medical doctor / researcher with a company that my family owned here in Stillwater, Minnesota, was a medical device manufacturer. And they worked with this guy who lives here in St. Croix Valley and started up a company called Diasorin, which has been very successful. And he was working in the lab for our family company. And I was trying to get him to embrace, a more systematic design of experiments approach. And I laid everything out for him. He never would do it, but he got good results. It just took him longer. Yeah. And one of the big things that I promote nowadays, because it's a selling point for R&D operations, is not so much that you'll get a more effective result by understanding interactions of things, but more of the multi-factor parallel processing being a way to more quickly get your research done and maybe complete a project in half the time that you would have otherwise. Yeah. So that's that's really a big selling point that I'm trying to promote. Even though secretly, as a chemical engineer, I'm more interested in the fact that you understand interactions and you get something greater than you would have otherwise. But the people that are running things, they just want to get it done faster.
Yeah. Thanks. So we have a few questions. So there's one I'll put up on the screen. So from Cassie, do you see the question, Mark?
Yes. The question about the Bayesian approach. I mean, this is going on, forever, right? Using prior knowledge to, bias the results basically that you're getting. I think, I looked at a little bit of Bayesian statistics as part of my master in business administration, and it really is very fascinating. But in the end, I'm not a Bayesian person. I'm going more with the opposite of it, which is the idea of the null hypothesis. You throw out your preconceived notions, and then you go through and do a study and only go to the alternative hypothesis if there's something significant occurring. So I'm a little bit suspicious of the Bayesian type of thing. And so at this point in time, Staties is not involved with that side of things.
Okay. And would you, so for example, you mentioned earlier, you have this kind of center point in your kind of hypercube of factors, right?
That's right.
And then you see, okay, well, if I go to this edge, right, where I use this combination of factors, I'm going up my yield function or whatever you're interested in.
Right.
Is there some validity or value to having a sort of semi-algorithmic way to kind of guide you on the response surface, or do you really just do an experiment, get an estimate of where you are on the response, and then do another experiment?
Yeah, I mean, we're working strictly empirical with our approaches. And we use, because there's multiple responses that you have to trade off, it gets really complicated. So we use something called desirability, where we rank each response on a ramp. If it's to be maximized, it's a 0 to 1 going up. If it's a minimized, 0 to 1 going down. If it's a specification, it's a tent function. And we can use desirability as an objective function to search through using a hill climbing approach once you fit all the models. And then you find something that hopefully is meeting your requirements, that's desirable, and then you're done. But there are a lot of other approaches, that can be deployed, and it's just that we're not really into that.
Okay, thanks for sharing. And thanks for the question, Cassie. I hope I'm pronouncing your name right. So there's another question. For some reason, I can't put it up on the screen, but I see it on my phone. So I'm just going to read it out. So it's from William. Does StatEase plan to incorporate gauge R&R capability? And if not, how come?
Yeah, I mean, we do have some capability with our StatEase 360 via the Python interface to do some things. But these gauge R&R studies, or I would call them variance component studies, as a certified quality engineer, before I could really do much of anything with manufacturing process improvement, I had to understand where the variability was coming from. In the chemical industry, it's a little bit different than with some hard goods that you don't actually have a gauge that or calipers that you're measuring things. But I did some essentially gauge R&R variance component studies to try to figure out what was the source of the variation. Was it the process? Was it the sampling? Or was it the test method? And through kind of a clever approach using secondary standards and some trickery with the manufacturing site, feeding in fake sample bottles and things like that, I was able to see that most of the variation was occurring in the test method. And that before we could really go any further, we had to work with the quality control group to get their test method to be producing accurate results. They were both inaccurate and imprecise. And it was impossible for us to continue on with our process improvement project before we address that. These variance component studies are nested and it's complicated statistically. We've had this gauge R&R idea in mind for a long time, but it's a smaller segment of the overall market for industrial R&D. You're getting into a different group of people that are more the certified quality engineers like myself. So at the moment, I don't foresee that we're going to have tools for that soon, but maybe someday.
Okay. Thanks for sharing. So I hope that answers your question, William. So we have about 2 minutes left. I would just like maybe, Mark, if you could very quickly just maybe rifle off a few resources or things that you think are good for people that are curious to get into the field, learn more about it. It could be books, it could be courses, it could be learning platforms, and then we can wrap up.
Yeah, I mean, I would love it if people would go to 3ws.staties.com and see all the resources we have. We have a huge repository of case studies, so that if you're thinking, well, has anybody applied design of experiments in my application, you'll probably find something there. You can go to our YouTube TV channel, and there's lots of recordings of various webinars about DOE. Obviously, the 3 simplified books, the trilogy of books, if you really are going to get going on that. And then, I just say, go ahead and start trying some things. Like I had amazingly a high school student that gave a talk at this conference I was a keynote speaker of earlier this month. She reached out and she said, well, I'm interested in, now that I've attended your presentation about design of experiments, to learn more about it. What should I do? I said, well, go in your kitchen and do a little experiment with your microwave popcorn machine. Try 2 different brands of popcorn 2 different times and just do it. Do a little experiment in your kitchen. And I think that's always the best approach to, learning something, is actually to try it and do it.
Yeah, that makes sense. Okay, so we'll just wrap up quickly. So thank you, Mark. I know that you wanted to announce about the DOE Summit. So maybe very, very quickly say when it's happening, who it's for, and I'll share the link right now for people who are interested.
Yeah, we've been doing these summits in Europe because there's a tremendous amount of collegiality, throughout our European users, and they could easily, show up at different sites. Like in Paris was the last one we had it. But nowadays it's hard to get the budget to travel. And so, of course, during the coronavirus, we pivoted over to doing things online for our training. And then we started doing these online DOE summits. So we have another one coming up here in June, and you can follow the link, but we've got a tremendous lineup of speakers. We've got for example, a fellow named Niels Decker from Axo Nobel, just as one example from industry, talking about how they've used DOE. At the Paris conference, we had a fellow from GlaxoSmithKline. And so I would highly encourage people to go to the site, enroll in this online summit, and attend some of these talks, if not all of them. And I think you'll really learn a lot from this. I'm excited about one from our UK operation, Prism Training and Consultancy, from Andrew McPherson, and he's going to talk about how to make really good coffee. So some practical ideas are going to come out of this.
Nice. Okay, sounds fascinating. It's on June 8th, if I recall.
Yeah, it's going to be a series of presentations over a period of time. So the best thing would be to go keep up with the schedule that we've posted, and then get onto it. Okay,
great. So thank you for your time. There's one more question we didn't have time to address. If you have other questions, keep them rolling in. We're gonna take time to answer in written form. So if people want to ask questions, you can reach out to me on LinkedIn. I'll be happy to answer. And I hope this was very useful to you. And Mark, thank you again for the time. This talk was great. I really loved the insights that you gathered over your career, and I'm happy you could share it with us.
Yeah, my pleasure. Thanks for inviting me, Justin.
All right, so we're going to stop here. So thanks everybody for attending. It was a lot of fun, and thanks for the questions. So stay tuned. We're going to answer some questions in the chat probably later. All right, thank you.
Take care.
Bye.